Let yourself settle in now. Find that position where your body can truly relax, where the weight of everything you're carrying begins to dissolve like morning mist in sunlight. Take a slow, deep breath through your nose. Hold it for just a moment, and then let it flow out gently through your mouth, releasing whatever tension has accumulated in your shoulders, your jaw, the space between your eyebrows. Tonight, we're going on a journey through the cosmos, but not one that requires anything from you except to simply be here, present, breathing, allowing the story to unfold like waves lapping at the shore of your consciousness. We're going to explore something profound, something that touches the very heart of what it means to be alive and aware in this vast, ancient universe. But there's no need to hold on to every detail or memorize every name. Just let the words wash over you, painting pictures in your mind of cosmic landscapes that stretch beyond imagination, of questions that have puzzled humanity since we first looked up at the night sky and wondered if someone, somewhere, was looking back. So breathe, relax, and let's drift together into the depths of space and time, where the great silence of the universe awaits with all its terrifying implications. The Great Silence. There's something deeply unsettling about silence when you expect to hear voices. Imagine walking into a crowded city where every building stands empty, where every street stretches vacant despite all evidence that people should be there. The infrastructure exists, the buildings are intact, the lights still work, but nobody's home. This is the situation humanity finds itself in when we consider the universe at large. We live in a cosmos that should be teeming with civilizations, echoing with the chatter of countless intelligent species, and yet we hear nothing but an eerie, profound silence. This contradiction has a name. Scientists call it the Fermi Paradox, named after the brilliant physicist Enrico Fermi, who, during a casual lunch conversation at Los Alamos National Laboratory in the summer of 1950, posed a deceptively simple question to his colleagues. They'd been discussing flying saucers and the possibility of faster-than-light travel, topics that might have seemed frivolous for some of the most brilliant minds of their generation. But then Fermi, with the kind of insight that made him one of the 20th century's greatest physicists, suddenly asked, "Where is everybody?" The question landed like a stone dropped into still water, ripples of implication spreading outward. His colleagues understood immediately what he meant. Given the age of the universe, roughly 13.8 billion years old, and given the sheer number of stars in our galaxy alone, somewhere between 100 billion and 400 billion suns, many of them older than our own, shouldn't we have encountered evidence of extraterrestrial civilizations by now? Shouldn't someone have visited us, contacted us, left some mark of their existence that we could detect? The mathematician Edward Teller, who was present at that lunch, recalled decades later how Fermi had done some quick calculations, scribbling numbers on a napkin, or perhaps just running them through his remarkable mind. Fermi concluded that Earth should have already been visited many times over by aliens. The fact that we hadn't been visited, or at least had no credible evidence of such visits, seemed to contradict everything probability suggested should be true. It was, in essence, a paradox, a logical contradiction that demanded explanation. To understand just how profound this paradox is, we need to consider the numbers involved. Let's start with a framework that's become foundational to discussions of extraterrestrial intelligence. In 1961, just 11 years after Fermi posed his question, astronomer Frank Drake was organizing the first scientific meeting on the search for extraterrestrial intelligence. He wanted a way to structure the discussion, so he developed an equation, a simple formula that broke down the probability of detecting alien civilizations into manageable components. This became known as the Drake equation. The equation looks deceptively simple. It multiplies together 7 different factors. First, the rate of star formation in our galaxy, how many new stars are born each year. Then, the fraction of those stars that have planets orbiting them. Next, the number of planets per solar system that could potentially support life. After that comes the fraction of those planets where life actually develops, followed by the fraction where that life evolves intelligence, and then the fraction where that intelligence develops technology capable of communicating across interstellar distances. Finally, there's the length of time such civilizations exist and remain detectable. When Drake first proposed this equation in 1961, many of these factors were complete unknowns. Astronomers could estimate star formation rates with some confidence, but planets around other stars hadn't been discovered yet. The first confirmed exoplanet orbiting a main sequence star wouldn't be found until 1995. Everything else about the equation was pure speculation, educated guesses based on the single data point we had: Earth. But here's what makes the equation fascinating and the paradox so troubling. Even with conservative estimates for each factor, the numbers suggest there should be many technological civilizations in our galaxy. Let's walk through this calculation using relatively cautious assumptions based on our current understanding. Our galaxy forms approximately 1.5 to 3 new stars every year. Recent discoveries by NASA's Kepler Space Telescope and other exoplanet hunting missions have revealed that planets are extraordinarily common. Nearly every star we've examined closely appears to have planets, so we can confidently set the fraction of stars with planets close to 1, meaning almost all of them. The number of planets per solar system in the habitable zone, that Goldilocks region where temperatures allow liquid water to exist on a planet's surface, is harder to pin down. But ongoing observations suggest perhaps 1 in 5 stars has at least one potentially habitable planet. That might sound low, but remember, we're talking about hundreds of billions of stars in our galaxy alone. Now, things get trickier. What fraction of those potentially habitable planets actually develop life? Here we have only one example: Earth. But life on Earth appeared remarkably quickly in geological terms. Within perhaps 1 billion years of Earth's formation, and possibly much sooner, life had taken hold. Some scientists interpret this as evidence that life emerges readily when conditions are right. Others argue that we're observing selection bias, that we only exist to ask the question because life happened to emerge here, and we have no way of knowing how, typical or atypical that is. Let's be conservative and say that 1 in 10 habitable planets develops life at some point. That still leaves us with billions of living worlds in the Milky Way. But most of that life might be microbial, simple organisms that never evolve beyond the bacterial stage. Earth spent roughly 3 billion years with only single-celled life before complex multicellular organisms appeared. Intelligence might be rare even among living worlds. Let's say only 1 in 100 worlds with life eventually evolves intelligent beings capable of understanding science and mathematics. Then comes technology. Intelligence alone isn't enough. A species needs to develop the means of sending signals into space or building structures large enough to be detected across interstellar distances. Tool use, societal cooperation, scientific curiosity, All these factors matter. Perhaps only 1 in 10 intelligent species develops detectable technology. Finally, there's the lifetime of such civilizations. How long does a technological society persist? Humanity has been broadcasting radio signals into space for barely more than a century, a cosmic eye blink. Will we still be here? Still be broadcasting in 1,000 years? 10,000? A million? This factor is perhaps the most uncertain of all, ranging from pessimistic estimates of a few hundred years to optimistic projections of billions of years. Even with these conservative numbers, multiplying them together suggests there should be thousands, perhaps tens of thousands of currently active, broadcasting civilizations in the Milky Way galaxy right now. And yet we've detected nothing. No radio signals, no optical beacons, no megastructures dimming distant stars in patterns that couldn't be natural. The universe maintains its great silence. This silence has been quantified through decades of systematic searching. The search for extraterrestrial intelligence, or SETI, began in earnest in 1960 when Frank Drake pointed a radio telescope at 2 nearby sun-like stars, Tau Ceti and Epsilon Eridani, listening for signals that might indicate intelligent origin. He detected nothing. Since then, SETI efforts have expanded dramatically, surveying millions of stars across multiple wavelengths, looking for any deviation from natural radio emissions that might suggest an artificial source. The Breakthrough Listen project, launched in 2015, represents the most comprehensive search effort to date. It's surveying the million closest stars to Earth, scanning the plane of our entire galaxy, and even looking at 100 nearby galaxies. The project uses some of the world's most powerful radio telescopes, including the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia, later adding the Meerkat Array in South Africa. As of 2025, Breakthrough Listen has examined more than 15,000 stellar pointings, collecting petabytes of data. They found no convincing evidence of extraterrestrial technology. Recent efforts have grown even more ambitious. The Very Large Array Sky Survey has scanned more than 950,000 unique pointings, setting power limits on potential transmissions. In April 2025, a deep SETI search of the TRAPPIST-1 system was conducted. This system, located just 40 light-years away, contains 7 Earth-sized planets, 3 of them in the habitable zone. It seemed like an ideal target. The 500-meter Aperture Spherical Telescope in China, the largest single-dish radio telescope in the world, observed TRAPPIST-1 for 1.67 hours, listening for signals between 1.05 and 1.45 gigahertz, with sensitivity down to 2.04 times 10 to the 10th watts. They found nothing. No technosignatures, no signs of artificial transmissions. The silence grows more profound with each null result. It's not that we've looked everywhere. Jill Tarter, one of the pioneers of SETI, has compared our search efforts to dipping a single glass into the ocean and finding no fish in that glass, concluding that the ocean contains no fish. We've barely scratched the surface of the possible search space. But given how many searches have been conducted, given how many targets have been examined, the continued absence of detections starts to feel significant. Some skeptics have argued that maybe we're looking in the wrong places or in the wrong ways. Perhaps alien civilizations don't use radio waves for communication. Maybe they've moved on to technologies we can't even imagine. Methods of communication that don't involve electromagnetic radiation at all. This is possible, of course, but it seems like special pleading. For any technological civilization to reach the point where they can develop exotic communication methods, they would presumably pass it through a radio broadcasting phase first. We should be detecting those signals from younger civilizations, even if the older ones have moved beyond them. Others suggest that intelligent life might be common, but that broadcasting into space is rare. Perhaps most civilizations realize that advertising their presence is dangerous and choose to remain silent. This idea has gained traction in recent years, particularly after Chinese science fiction author Liu Cixin popularized what he called the dark forest hypothesis in his novel The Dark Forest. But we'll return to that particular terrifying possibility later. For now, what matters is this. The Great Silence is real. It's been quantified through systematic observation, and it demands explanation. Somewhere, somehow, our assumptions must be wrong. Either life is far rarer than we think, or intelligence is harder to evolve than we imagine, or technological civilizations inevitably destroy themselves, or they're hiding from us, or something else is going on that we haven't even conceived of yet. This is the Fermi Paradox, and it stands as one of the deepest mysteries in science. It's not just an academic puzzle. It's a question that touches on humanity's place in the cosmos, on our future, on the very meaning of intelligence and consciousness in a universe that seems to have produced precious little of either. The silence of the stars isn't just puzzling, it's profoundly, existentially unsettling. Because every explanation that resolves the paradox carries disturbing implications. And the most unsettling thought of all is that the universe might be empty for a reason, and that reason might be something that awaits us in our own future. Cosmic Timescales and the Rare Earth Hypothesis. To truly grasp why the silence is so strange, we need to develop an intuition for the vast timescales involved in cosmic evolution. The universe didn't just pop into existence yesterday. It's old, unimaginably old, and that age should work in favor of abundant life. The Big Bang occurred 13.8 billion years ago. For comparison, our entire solar system is only about 4.6 billion years old. The Earth has existed for roughly 4.54 billion years. Complex multicellular life emerged around 600 million years ago. Our species, Homo sapiens, has existed for approximately 300,000 years. Civilization, as we'd recognize it, with agriculture and cities and writing, is only about 10,000 years old. And we've had the capacity to detect radio signals from space for less than 70 years. Put another way, if we compressed the entire history of the universe into a single year, with the Big Bang occurring at the first second of January 1st, our solar system wouldn't form until September. Complex life on Earth wouldn't appear until mid-December. Humans wouldn't arrive until 11:58 p.m. on December 31st. All of recorded human history would take place in the final few seconds before midnight. The point is that the universe had an enormous head start. Stars were forming, solar systems were coalescing, potentially habitable planets were cooling down and developing atmospheres billions of years before Earth even existed. If life is common, if intelligence evolves readily, then there should be civilizations out there that are millions or even billions of years older than ours. Think about what that means. Human technological civilization is barely 200 years old if we date it from the Industrial Revolution. In that brief span, we've gone from steam engines to nuclear power, from the telegraph to the internet, from horse-drawn carriages to spacecraft exploring the outer solar system. Imagine a civilization with a million-year head start on us. What would they be capable of? What technologies would they possess? What structures might they build? The physicist Freeman Dyson famously proposed that truly advanced civilizations might build megastructures around their stars to capture all available solar energy. These Dyson spheres, or Dyson swarms, would be detectable from enormous distances, as they would absorb visible light from the star and re-radiate it as infrared heat. Astronomers have actually looked for evidence of such structures. They've found none. No anomalous infrared signatures that can't be explained by natural processes like dust clouds or planetary formation. Some researchers have suggested that maybe we're not seeing these megastructures because advanced civilizations transcend their physical origins, uploading themselves into computers or exploring virtual realities rather than expanding physically across space. Or perhaps they pursue goals we can't comprehend with our primitive understanding. But these explanations feel like we're adding epicycles, creating increasingly complex scenarios to explain why we don't see what probability suggests we should see. This is where the rare Earth hypothesis enters the picture. Perhaps the resolution to the Fermi Paradox is much simpler than exotic explanations about transcendent civilizations. Perhaps Earth isn't typical at all. Perhaps life, especially complex life, is extraordinarily rare. The hypothesis was articulated most fully in a 2000 book by geologist Peter Ward and astronomer Donald Brownlee called Rare Earth: Why Complex Life is Uncommon in the Universe. They argued that while simple microbial life might be common, the conditions necessary for complex multicellular life to evolve are vanishingly rare. Earth, they suggested, won the cosmic lottery, blessed with a confluence of factors that are unlikely to occur together on most planets. Let's examine some of these factors, because they're genuinely remarkable when you start listing them. First, there's our location in the galaxy. The Milky Way isn't a uniform environment. Closer to the galactic center, stars are packed more densely together. This increases the likelihood of gravitational perturbations that could destabilize planetary orbits, flinging planets out of their habitable zones, or even out of their solar systems entirely. The galactic center also hosts a supermassive black hole and generates more radiation. Gamma-ray bursts, those catastrophic stellar explosions we'll discuss in more detail later, are more common in the dense galactic core. Earth orbits in what some astronomers call the galactic habitable zone, a ring-shaped region roughly 23,000 to 29,000 light-years from the galactic center, where conditions are relatively calm and stable. We're in the suburbs of the galaxy, a quiet neighborhood where cataclysmic events are less frequent. Recent research has suggested that planets in the inner regions of the galaxy, where 25% of the galaxy's stars reside, faced more than a 95% chance of being sterilized by a lethal gamma-ray burst within the past billion years. Life as we know it could survive with certainty only in the galactic outskirts. But our fortunate galactic location is just the beginning. Consider our solar system. We have Jupiter, a gas giant with more mass than all the other planets combined. Jupiter acts as a cosmic vacuum cleaner, its immense gravity deflecting or capturing asteroids and comets that might otherwise rain destruction on the inner planets. Computer simulations suggest that without Jupiter, Earth would be bombarded by potentially life-ending impacts far more frequently. Too many such impacts and complex life never gets the stable environment it needs to evolve. Then there's our moon. Earth has an unusually large moon for a rocky planet, almost certainly formed by a Mars-sized object colliding with the early Earth in a titanic impact. That moon stabilizes Earth's axial tilt, preventing wild swings in climate that could occur if our planet wobbled chaotically. The moon also drives tides, which may have played a crucial role in the transition of life from ocean to land by creating tidal pools where evolutionary innovations could develop. We're also fortunate in our star. The Sun is a relatively stable, long-lived star. It doesn't flare violently like many red dwarfs, the most common type of star in the galaxy. Red dwarfs can emit powerful stellar flares that would sterilize the surfaces of nearby planets. For a planet to be in a red dwarf's habitable zone, it needs to orbit close to the star within the range of these deadly flares. Recent research on TRAPPIST-1, despite its promising 7 Earth-sized planets, has raised concerns about the volatility of red dwarf stars and whether their planets could truly support life. Earth's atmosphere is another marvel. We have just the right mix of gases, maintained by the presence of life itself in a kind of feedback loop. Our magnetic field, generated by our planet's molten iron core, shields us from solar wind and cosmic radiation. Mars lost its magnetic field early in its history, and the solar wind stripped away most of its atmosphere, leaving it cold and dry. But perhaps the most intriguing factor relates to Earth's geology. In 2024, researchers Robert Stern and Taras Garia published findings that suggested plate tectonics might be essential for complex life. Earth is the only planet in our solar system with active plate tectonics, the process by which the planet's crust breaks into plates that move, collide, and slide past each other. Plate tectonics does several things that might be crucial for life. It drives the carbon-silicate cycle, a thermostat that regulates atmospheric carbon dioxide over geological timescales, preventing the planet from either freezing solid or heating into a runaway greenhouse. Plate tectonics creates diverse environments, continents and ocean basins, mountains and valleys, providing the variety of habitats that drives evolutionary innovation. The process also recycles nutrients, bringing minerals from the deep earth to the surface where life can access them. Stern and Garia calculated that for a planet to have both continents and oceans, which seems necessary for the kind of biodiversity we see on Earth, the planet needs to have between 0.007 and 0.027% of its mass in water. Too much water, and you have a world-spanning ocean with no land. Too little, and you have a desert planet. That's a narrow window. They also estimated that only about 33% of planets have the right composition to form sufficiently dense tectonic plates, and of those only about half are large enough with sufficient gravity to sustain plate tectonics over geological time. When Stern and Garia incorporated these factors into a modified Drake equation, they found that the chance of a planet having the right conditions for complex life dropped to somewhere between 0.0034% and 0.17%. This suggests there could be anywhere from as few as 0.006 to as many as 100,000 active, communicating civilizations in our galaxy. The low end of that range is close to 0, implying we might genuinely be alone in the Milky Way. There's also the crucial factor of timing. For the first few billion years of the universe's existence, the cosmos was a more violent place. Galaxies were smaller, stars were packed more closely together, and stellar explosions were more common. Life might not have been able to gain a foothold. Some calculations suggest that complex life could only have safely developed within the past 5 billion years, after the universe had calmed down sufficiently. And even once life emerges, it faces obstacle after obstacle. On Earth, life spent roughly 3 billion years as nothing more than single-celled organisms. For 3/4 of life's existence on this planet, nothing more complex than bacteria existed. Then, in an event called the Cambrian explosion, around 540 million years ago, complex multicellular life suddenly diversified. We still don't fully understand what triggered this explosion of diversity. It might have been a rise in atmospheric oxygen levels, or changes in ocean chemistry, or the evolution of predation driving an evolutionary arms race, or some combination of factors. Whatever the cause, it was a crucial transition, and it took 3 billion years to occur. Intelligence is even rarer. Life on Earth has produced millions of species over billions of years. Only one, as far as we know, has developed the kind of abstract reasoning, language, and technology that we'd call intelligence. Even among our closest relatives, the great apes, the cognitive gap is enormous. Chimpanzees can use tools and have rudimentary culture, but they've never discovered fire or invented agriculture or developed writing. Some scientists have suggested that intelligence might not be as advantageous as we like to think. It's metabolically expensive. The human brain consumes about 20% of our body's energy despite making up only 2% of our mass. For most of Earth's history, most ecological niches have been successfully filled by non-intelligent organisms. Sharks have been apex predators for hundreds of millions of years without needing to understand calculus. Intelligence seems to be one possible evolutionary strategy among many, not an inevitable outcome of evolution. All of this suggests that the emergence of intelligent, technological life might indeed be extraordinarily rare. If you stack up all the requirements, all the fortunate circumstances that seem necessary, the probability becomes vanishingly small. Perhaps Earth really is one in billions, a cosmic fluke, and the universe is mostly empty of the kind of complex life that could build civilizations and ask questions about their place in the cosmos. The rare Earth hypothesis is comforting in some ways. It suggests that we're special, that our planet and our species are genuinely unique. But it's also deeply isolating. If complex life is truly rare, then we're profoundly alone in a vast, mostly dead universe. The stars aren't silent because civilizations are hiding. They're silent because there's no one there to make noise. And if that's true, then the responsibility that falls on humanity becomes almost unbearable. We might be the only witnesses, the only consciousness, the only beings capable of understanding the universe. If we destroy ourselves, we don't just end human civilization. We might be extinguishing the only light of awareness in an otherwise dark cosmos. The great filters, possible explanations. But what if life isn't so rare? What if the universe is actually teeming with living planets, but something prevents those living worlds from developing into spacefaring civilizations? This brings us to one of the most influential and disturbing ideas in modern astrobiology, the concept of the Great Filter. The Great Filter hypothesis was proposed by economist Robin Hanson in 1996. It's an attempt to reconcile the Fermi Paradox by suggesting that there's some kind of barrier, some incredibly difficult step or series of steps that prevents the emergence of spacefaring civilizations. The filter acts like a cosmic sieve, allowing only a tiny fraction of potential civilizations to pass through. Here's what makes this concept so unsettling. The filter has to be somewhere in the sequence of events that leads from a barren planet to a civilization capable of colonizing the galaxy. It could be behind us, meaning we've already passed through it, which would be wonderful news. Or it could be ahead of us, meaning we're approaching it, and it's likely to destroy us. The silence of the universe suggests that very few civilizations make it through, which means the filter must be extraordinarily effective at eliminating potential competitors. Let's think about where this filter might be. One possibility is that it's very early in the sequence. Maybe the origin of life itself is the great filter. Perhaps the jump from non-living chemistry to self-replicating, evolving organisms is so improbable that it happens only once in billions of planets. In July 2025, physicist Robert Andres at Imperial College London published a mathematical framework that calculated the probability of a protocell, the simplest self-replicating structure capable of evolution arising spontaneously. Using information theory and algorithmic complexity, Andres showed that this probability is astronomically low. The random assembly of a protocell is like randomly typing a scientific article letter by letter. As complexity grows, the probability of success plummets toward zero. If Andres is right, then abiogenesis, the origin of life, might be the great filter. In that case, we've already passed it, and the hard part is behind us. But Earth's history doesn't seem to support this being the filter. Life appeared on Earth remarkably quickly. The planet formed about 4.54 billion years ago. For the first few 100 million years, it was a hellscape, bombarded by asteroids with surface temperatures high enough to melt rock. But as soon as conditions became even remotely hospitable, perhaps as early as 4.1 billion years ago, life appeared. Within a billion years of Earth's formation, we have evidence of living organisms. If life emerges that quickly when conditions allow, it suggests that abiogenesis might not be as difficult as Andres's calculations suggest. Perhaps there's something about chemistry we don't understand. Some pathway from non-living to living matter that's more accessible than we think. So maybe the filter is later. Perhaps it's the transition from simple single-celled life to complex multicellular organisms. This transition did take a very long time on Earth. For 3 billion years, life remained stubbornly simple. Then, relatively suddenly, complex life appeared. This suggests that the jump to multicellularity might be genuinely difficult, requiring a precise confluence of environmental and evolutionary factors. A 2024 study linked the Cambrian explosion to Earth's transition from a single-lid tectonic regime to modern plate tectonics. For the first billion years or more of complex life, Earth's crust was static, and evolutionary diversification stalled. Once plate tectonics activated, creating diverse environments and cycling nutrients, life exploded in complexity. If plate tectonics is rare, as the Stern and Garia study suggests, then perhaps this transition to complex life is where the great filter lies. Or maybe the filter is even later. Maybe complex life is common, but intelligence is rare. We've discussed how intelligence seems to be just one evolutionary strategy among many, not a universal goal of evolution. Most successful species throughout Earth's history have been non-intelligent. Dinosaurs ruled the planet for 165 million years without developing technology. If a gamma-ray burst had sterilized Earth 200 million years ago, the universe would never have known that intelligence had been a possibility here. Perhaps on most planets with complex life, evolution simply never takes the path that leads to sapience. But if we've made it this far, if intelligence has evolved, surely the hardest part is over, right? Maybe not. Perhaps the great filter isn't behind us at all. Perhaps it's ahead of us, waiting in our future, and that's why the universe is silent. Maybe technological civilizations inevitably destroy themselves, and we're about to discover why. This possibility is genuinely terrifying, because it fits the evidence so well. If every civilization that develops technology goes on to destroy itself shortly afterward, that would perfectly explain the Great Silence. We wouldn't see alien civilizations because they don't last long enough to spread across the galaxy or leave detectable traces. And if this is true, it means we're likely heading toward that same fate. What might this filter look like? The most obvious possibility is nuclear war. Humanity developed nuclear weapons in 1945. Within a few years, we had enough warheads to destroy human civilization many times over. We came frighteningly close to using them during the Cuban Missile Crisis in 1962. Even today, thousands of nuclear warheads remain on hair-trigger alert, capable of launching within minutes. One mistake, one miscommunication, one malfunction in aging infrastructure, and we could still trigger a nuclear holocaust that renders Earth uninhabitable. But nuclear war is just one possibility. Maybe the filter is climate change. We're conducting an unprecedented experiment on our planet's atmosphere, burning fossil fuels at a rate that would have seemed impossible a century ago, adding greenhouse gases faster than natural processes can remove them. We're altering weather patterns, melting ice sheets, acidifying oceans, and triggering cascading changes whose ultimate consequences we can't fully predict. Maybe most civilizations do this, burning through their planet's resources in a brief frenzy of industrialization before the environmental catastrophe they've created wipes them out. Or perhaps the filter is biological. Maybe every technological civilization eventually develops biotechnology sophisticated enough to modify viruses and bacteria, and inevitably someone creates a pathogen that escapes containment and devastates their species. We're advancing rapidly in genetic engineering, synthetic biology, and our understanding of how to manipulate living systems. It's entirely possible that within this century, a small group of people, or even a single individual, could engineer a supervirus that human immune systems couldn't combat. Artificial intelligence presents another possible filter. We're working toward creating general artificial intelligence, systems that can match or exceed human cognitive capabilities across all domains. Most AI researchers believe this is achievable within the next few decades, perhaps within this century. But what happens when we create an intelligence vastly superior to our own? If we fail to align its goals with human values, if we lose control of the development process, an advanced AI could view humanity as either irrelevant or as a threat to be eliminated. This sounds like science fiction, but computer scientists working on AI safety take it seriously. Stuart Russell, one of the field's pioneers, has warned that superintelligent AI could pose an existential risk to humanity if we're not extraordinarily careful. There might be even more exotic filters we haven't considered. Maybe there's something fundamentally self-limiting about technological advancement. Perhaps any civilization that achieves a certain level of technology inevitably falls into a trap of some kind, a failure mode we can't even imagine yet. The philosopher Nick Bostrom has suggested that there might be discoveries that are so dangerous that making them guarantees destruction, what he calls a black ball drawn from the urn of possible knowledge. Nuclear weapons might be one such discovery. There might be others, worse ones, waiting to be uncovered by any species that pushes the boundaries of physics and engineering far enough. Game theory offers another disturbing possibility through what's called the burnout hypothesis. Researchers Michael Wong and Stuart Bartlett proposed in 2022 that civilizations might face what they called asymptotic burnout. As civilizations grow and their energy consumption scales up, they face increasingly frequent crises that require ever more rapid innovation to survive. Eventually, the pace of required innovation exceeds what's possible, and the civilization collapses. If this model is correct, any civilization might be doomed to either collapse from burnout or undergo what they called a homeostatic awakening, redirecting themselves away from growth and toward sustainability, which would make them invisible to our current detection methods. The truly terrifying aspect of the Great Filter hypothesis is its implications for humanity. If the filter is behind us, if we've already passed through the hardest part, then we might be one of the first civilizations to make it this far. That would be wonderful, in a sense. It would mean the future is open, the galaxy is ours to explore and settle. But it also means we're utterly alone, at least for now. If the filter is ahead of us, though, then our future is bleak. The silence of the universe becomes a warning. Every dead planet, every extinguished civilization that came before us encountered something that destroyed them. And we're walking toward that same fate, blind to the danger because we don't know what form it will take. The stars aren't silent because civilizations are rare or hiding. They're silent because no one makes it past a certain point. Everyone dies. There's no way to know which scenario is correct without more data. We'd need to find evidence of life, even simple life, on other planets to determine if the origin of life is as difficult as some suggest. We'd need to detect biosignatures from planets with complex ecosystems to know if the jump to complex life is the filter. And if we find evidence that life and even complex life is common, but still see no signs of technological civilizations, that would be the most frightening discovery of all. It would strongly suggest that the Great Filter is ahead of us, that something about reaching technological maturity is fundamentally incompatible with long-term survival. Until then, we live with uncertainty and the weight of what that uncertainty might mean. The universe's silence might be trying to tell us something. It might be screaming a warning that we're too primitive or too proud to hear. And the terrifying possibility is that by the time we understand the message, it will already be too late. Dark forest theory and cosmic predation. Let's consider a different possibility, one that's arguably even more disturbing than the Great Filter. What if the universe isn't empty at all? What if it's full of intelligent civilizations, but they're all hiding, maintaining strict radio silence, because making your presence known in this cosmos is tantamount to suicide? This is the essence of the dark forest hypothesis, named after the second book in Chinese science fiction author Liu Cixin's Remembrance of Earth's Past trilogy. In Liu's novel, the hypothesis is explained through a character named Ye Wen-jie, who derives it from what she calls the axioms of cosmic sociology. The argument goes something like this. First axiom: survival is the primary need of every civilization. Everything else, all other values and goals, are secondary to continuing to exist. Second axiom: civilizations continuously grow and expand over time, but the total matter in the universe remains constant. This means there's fundamental competition for finite resources. From these axioms, along with two crucial assumptions about the nature of interstellar communication and the speed of technological growth, flows a chilling conclusion. When a civilization discovers another civilization, it faces a profound problem. It cannot know the other civilization's true intentions. Communication is slow because of the vast distances involved. Light itself takes years to travel between stars. By the time you send a message and receive a response, decades might have passed, during which the other civilization could have developed. From these axioms, along with two crucial assumptions about the nature of interstellar communication and the speed of technological growth, flows a chilling conclusion. When a civilization discovers another civilization, it faces a profound problem. It cannot know the other civilization's true intentions. Communication is slow because of the vast distances involved. Light itself takes years to travel between stars. By the time you send a message and receive a response, decades might have passed, during which the other civilization could have developed. From these axioms, along with two crucial assumptions about the nature of interstellar communication and the speed of technological growth, flows a chilling conclusion. When a civilization discovers another civilization, it faces a profound problem. It cannot know the other civilization's true intentions. Communication is slow because of the vast distances involved. Light itself takes years to travel between stars. By the time you send a message and receive a response, decades might have passed, during which the other civilization could have developed weaponry capable of destroying you. Even if the other civilization seems peaceful in its communications, you can't be certain. They might be lying, or they might be peaceful now but become aggressive later. Or there might be a third party out there, observing both of you, who sees your communication as a threat. The uncertainty is insurmountable. Moreover, Liu argues that technological growth creates what he calls chains of suspicion. Even if Civilization A knows that Civilization B is benevolent, A cannot be sure that B knows that A is benevolent. And even if both civilizations understand each other's peaceful nature, neither can be certain that a third civilization C, observing them, understands that they're both peaceful. Each additional link in this chain of understanding makes trust exponentially more difficult. The safest strategy, then, given these conditions, is devastatingly simple. If you detect another civilization, you destroy it immediately, before it can become a threat to you. You strike first because waiting carries unbearable risk. You don't communicate, you don't negotiate, you don't try to understand. You eliminate the potential threat while you still can. The universe, in this view, resembles a dark forest at night. Every civilization is a hunter, creeping through the trees with a loaded weapon, knowing that somewhere in the darkness there are other hunters. The moment you make a sound, the moment you light a fire that reveals your position, you paint a target on yourself. The only way to survive is to stay hidden, to remain perfectly silent, to hunt without being hunted. Any civilization foolish enough to broadcast its existence, to send signals into space announcing, "Here we are," has signed its own death warrant. This explains the Great Silence perfectly. The universe isn't empty. It's full of hiding civilizations, all terrified to reveal themselves, all watching and waiting in the darkness. Humanity, in our ignorance, has been shouting into the void for a century, broadcasting radio and television signals that proclaim our existence to anyone listening. We've even sent deliberate messages to the stars, like the Arecibo message beamed toward the globular cluster M13 in 1974. From the dark forest perspective, these actions are monumentally foolish, like a child screaming in a forest full of predators. The hypothesis is game-theoretically sound, at least under certain assumptions. It draws on the prisoner's dilemma and similar scenarios from game theory, where cooperation is rational, but paranoia is safer. When communication is slow and verification is impossible, when the cost of being wrong is extinction, the Nash equilibrium, the stable strategy that survives, is preemptive destruction. But is it realistic? Does the dark forest hypothesis actually explain the silence we observe? There are several arguments against it. First, it assumes that civilizations inevitably become more paranoid and aggressive as they advance. But Earth's history suggests the opposite might be true. As human societies have developed, we've generally moved toward greater cooperation, larger political entities, and international institutions designed to prevent conflict. Wars between developed nations have become increasingly rare. Perhaps advanced civilizations outgrow the paranoia that the dark forest hypothesis requires. Second, the hypothesis assumes that destroying another civilization across interstellar distances is feasible. In Liu's novels, this is accomplished through relativistic projectiles, small objects accelerated to near light speed that impact targets with devastating kinetic energy. But such weapons would require enormous energy expenditures and would still take years or decades to reach their targets. A civilization capable of building such weapons would presumably be capable of detecting them and defending against them. The hunter in the dark forest might reveal their position by firing their weapon, making themselves vulnerable to counterattack. Third, there's the question of whether the first strike really is advantageous. If Civilization A attacks Civilization B, but B survives the initial attack or has automated defenses that continue operating, then A has created an implacable enemy that knows exactly where A is located and has every motivation to retaliate. Unless the first strike is guaranteed to be absolutely successful, completely annihilating the target civilization with no survivors and no automated systems left to carry on the fight, attacking might be more dangerous than maintaining peaceful silence. Furthermore, the hypothesis requires that all civilizations operate under these assumptions. If even a small percentage of civilizations are genuinely benevolent and choose to communicate openly despite the risks, we should still detect some signals. The absolute silence we observe would require not just that most civilizations are hiding, but that literally all of them are, or that the benevolent ones have all been exterminated, which would suggest that the universe has already gone through a dark forest phase that somehow cleaned out all the cooperative civilizations. That's possible, but it requires additional assumptions. Some scientists have proposed what we might call the dark forest light scenario. Perhaps civilizations do hide, not because they fear immediate destruction, but because they recognize that revealing themselves carries long-term risks. Even if most civilizations are peaceful, even if the probability of encountering a hostile civilization is small, the consequences of that encounter could be catastrophic. Why take the risk when there's no compelling need to broadcast? This modified version of the hypothesis suggests that mature civilizations practice what we might call cosmic quiet. They don't necessarily hide all traces of their existence. That might be impossible once you reach a certain level of development, but they don't advertise either. They conduct their business without shouting about it, and they certainly don't send targeted messages toward other star systems announcing their presence. If this is true, then humanity's broadcasts might not have condemned us yet. We haven't been transmitting for very long, and our signals are actually quite weak. By the time they've traveled a few dozen light years, they're indistinguishable from background noise. Any civilization detecting them would need sensitive equipment and would need to be looking specifically in our direction. But our recent activities, like the James Webb Space Telescope's observations and our plans for increasingly powerful radio transmitters, might be making us more visible. Some scientists have suggested that there should be a global conversation about whether we should continue or even intensify our attempts to contact extraterrestrial intelligence, given the potential risks. The dark forest hypothesis is compelling because it takes the game theory seriously and because it offers a complete explanation for the Fermi Paradox. But it's also deeply cynical, requiring us to believe that intelligence inevitably leads to paranoia and that cooperation is impossible on a cosmic scale. It suggests that the universe is not just indifferent to life, but actively hostile, a killing field where the only hope for survival is to hide and to strike first when necessary. If the dark forest hypothesis is correct, then the silence of the universe isn't peaceful. It's the tense, fearful silence of prey animals freezing when they hear a predator nearby. And humanity, in our naivety, has been dancing and singing, oblivious to the danger we might have created. The most terrifying part is that we won't know if we've made a fatal mistake until it's too late, until something arrives from the darkness between the stars, and by then there will be nothing we can do except realize, in our final moments, that the universe was empty for a reason, and we were too foolish to stay hidden. The Grabby aliens and expansion models. Let's shift perspectives to consider another explanation for the Great Silence, one that's less about filters and predators and more about simple timing and geometry. This is the Grabby aliens model, proposed by economist Robin Hanson, the same person who articulated the Great Filter Hypothesis. The Grabby aliens model starts with a different assumption. Instead of asking why we don't see aliens, it asks, if there are expanding civilizations out there, what would we expect to observe, and where are we most likely to be in space and time relative to them? The model assumes that some civilizations, perhaps a small fraction of all that ever arise, become what Hansen calls loud and grabby. These civilizations don't just develop technology and then sit quietly on their homeworld. They expand, sending out probes or colonies, or perhaps even relocating their entire civilization to other star systems. They modify their environment in visible ways, building Dyson spheres or other megastructures, perhaps even altering stars or rearranging solar systems to suit their needs. They grab up the resources around them, and they're loud about it, creating signals and changes that can be detected across vast distances. Now, here's the key insight. If such civilizations exist and expand at a significant fraction of the speed of light, they would eventually fill the universe. The cosmos isn't infinite in the sense that light has only had 13.8 billion years to travel since the Big Bang. There's a cosmic horizon beyond which we can't see because the light hasn't had time to reach us yet. Similarly, if expanding civilizations are out there, the universe should eventually be divided up into their expanding spheres of influence. Hansen and his collaborators, including Daniel Martin, Calvin McCarter, and Jonathan Paulson, developed a mathematical model published in 2021 that makes specific predictions. If we assume that Grabby civilizations appear randomly in space and time according to a power law distribution, that they expand at some fraction of light speed, and that once they meet, their boundaries stabilize, Then we can calculate how many such civilizations should exist and where we're likely to be relative to them. The model makes a striking prediction. We should not expect to see any Grabby aliens yet. The reason is simple. If Grabby civilizations were close to us in space, we'd likely be inside one of their expanding spheres by now, and we'd know it. The fact that we're here, observing from our quiet corner of the Milky Way, having arisen independently rather than being absorbed by someone else's expansion, tells us that we must be relatively early in cosmic history and relatively far from the nearest Grabby civilization. The model estimates that the nearest Grabby civilization is probably hundreds of millions of light years away, possibly billions. They won't reach us for tens of millions of years, at minimum, possibly much longer. We're in what Hansen calls a hard step filter scenario. There are difficult steps in the evolution from lifeless planets to expanding civilizations, steps so hard that they take a long time to occur even under favorable conditions. The fact that we exist now, roughly 13.8 billion years after the Big Bang, tells us something about how long these hard steps typically take. If most civilizations take billions of years to arise after the Big Bang, as we apparently have, then the universe is still relatively young in terms of civilization time. The first Grabby civilizations might be just now beginning their expansions, or they might have started expanding already but haven't reached us yet because space is so vast. Within a few 100 million years, cosmically a blink of an eye but far beyond any timescale humans can directly comprehend, the observable universe will be divided among these expanding empires. But right now, in this particular epoch, we're in a quiet period between the emergence of the first civilizations and their eventual meeting. This model is oddly comforting in some ways. It suggests that we're not doomed, not facing an imminent filter, not hiding from dark forest predators. We're simply early, one of the first civilizations to arise. The silence isn't ominous, it's expected. We should only be worried if we started detecting signs of Grabby civilizations nearby, because that would mean we were wrong about being early, and something else must explain why we arose independently rather than being absorbed. But there are concerning implications too. If this model is correct, it means that eventually civilizations will expand to fill all available space. The era of empty cosmos, of unexplored frontiers, of free real estate just waiting to be settled, is temporary. If humanity wants to be a Grabby civilization ourselves, if we want to ensure our long-term survival and expansion beyond Earth, we need to start moving outward relatively soon in cosmic terms. There's also the question of what happens when Grabby civilizations meet. The model assumes their boundaries stabilize, but why would that be? Do they negotiate, fight, merge? The model doesn't specify, leaving that as an open and potentially troubling question. Robin Hansen has argued that the Grabby aliens model makes testable predictions. We should be more likely to find ourselves at a particular moment in cosmic history and at a particular distance from the cosmic frontier, which the model can calculate. As we collect more data about the formation rates of planets, the frequency of life, and other factors that constrain when and where civilizations arise, we can refine the model's predictions and test whether our existence fits the pattern it predicts. One interesting prediction: we should be relatively early not just in cosmic time, but also in our galaxy's history of civilization. If Grabby civilizations expand throughout their galaxies before expanding to other galaxies, then we should be near the beginning of the Milky Way's civilization era. This fits with what we observe. We see no evidence of extensive modification of our galaxy, no Dyson swarms around millions of stars, no restructured solar systems. The galaxy appears pristine, untouched by technological intervention, which is what we'd expect if civilizations like ours are among the first to arise. But this raises a profound question. If we're early, if we're potentially one of the first civilizations in our galaxy, what's our responsibility? Do we have an obligation to become a Grabby civilization ourselves, to spread life and intelligence throughout the Milky Way? Or should we practice cosmic restraint, leaving other solar systems untouched in case other civilizations arise later who might want them? These questions don't have obvious answers. They venture into philosophy and ethics as much as science. But they're questions that might matter enormously for the long-term future of humanity and perhaps for the long-term future of the galaxy itself. The Grabby aliens model offers a resolution to the Fermi Paradox that's relatively optimistic. We don't see aliens because we're early, because space is vast, and because any expanding civilizations are still too far away to have reached us. But it's not entirely comforting either. It suggests that the current state of affairs, this era of exploration and possibility, is temporary. Eventually, the universe will be carved up among whoever manages to expand first and fastest. The cosmic land rush is coming, and humanity is either poised at the starting line or already hopelessly behind, depending on whether other civilizations got started before us. The silence of the universe in this interpretation isn't empty. It's pregnant with potential, a calm before a storm of expansion and growth that will eventually fill the cosmos with intelligence and purpose. Whether that future includes humanity or whether we'll be left behind. Spectators to the ambitions of others depends on choices we make in the coming centuries. The universe is empty for now, but it won't stay that way forever. Cosmic accidents and existential threats. While we've been discussing civilizations, their choices, and their potential fates, we've largely assumed that their extinction, if it occurs, is somehow their own fault, the result of war or environmental collapse or other self-inflicted wounds. But the universe is not a safe place. There are phenomena out there, entirely natural processes, that could extinguish civilizations without warning, without mercy, and without any possibility of prevention by species at our current level of technological development. Let's explore some of these cosmic catastrophes, because they might be part of the answer to why the universe seems so empty. Start with gamma-ray bursts, or GRBs. These are the most energetic events known in the universe, since the Big Bang itself. A gamma-ray burst releases more energy in a few seconds than the Sun will emit over its entire 10 billion-year lifetime. The radiation is so intense that a GRB occurring in our galaxy could sterilize Earth from thousands of light-years away. There are two types of gamma-ray bursts. Long-duration GRBs, lasting more than 2 seconds, are associated with the collapse of massive stars into black holes, a specific type of supernova called a collapsar. Short-duration GRBs, lasting less than 2 seconds, result from the merger of compact objects like neutron stars or a neutron star and a black hole. Both types produce narrow jets of gamma rays that, if pointed in your direction, deliver a devastating dose of radiation. If a gamma-ray burst occurred within several thousand light-years of Earth, and its jet was aimed at us, the effects would be catastrophic. The initial burst would strip away the ozone layer on the side of Earth facing the burst. Without ozone to absorb ultraviolet radiation, the Sun's UV light would sterilize the surface. The gamma rays would also split nitrogen molecules in the atmosphere, creating nitrogen oxides that would cause a persistent depletion of ozone lasting for years. The resulting UV exposure would devastate ecosystems, killing plankton in the oceans and destroying the base of the food chain. Research published in 2024 suggests that the inner regions of our galaxy, where 25% of the stars reside, faced more than a 95% chance of being sterilized by a gamma-ray burst within the past billion years. This makes the galactic habitable zone, the ring-shaped region where Earth resides, even more important. We are fortunate to be far enough from the galactic center that GRBs are rare. But we're not immune. Estimates suggest that Earth has been hit by a GRB capable of causing significant ozone depletion approximately once every several hundred million years. There's some evidence that a GRB may have contributed to a mass extinction event 450 million years ago. The Ordovician-Silurian extinction event eliminated about 85% of marine species. While the primary cause was likely a series of glaciations, some researchers have suggested that a nearby GRB could have triggered the initial cooling by depleting the ozone layer and altering atmospheric chemistry. But gamma-ray bursts are just one thread. Supernovae, the explosions of massive stars at the end of their lives, are less energetic than GRBs but more common. A supernova within 30 light-years of Earth could damage the ozone layer and irradiate the surface. Fortunately, there are no candidate stars that close to us likely to go supernova in the near future. The nearest potential supernova candidate is Betelgeuse, about 550 light-years away, far enough that its eventual explosion will be a spectacular light show, but not a threat to life on Earth. Then there are asteroid and comet impacts. We know that large impacts can cause mass extinctions. The Chicxulub impact 66 million years ago, which killed the non-avian dinosaurs, involved an asteroid roughly 10 kilometers in diameter. The impact released energy equivalent to billions of nuclear weapons, caused global fires, and threw so much debris into the atmosphere that photosynthesis shut down for years, collapsing ecosystems worldwide. Earth gets hit by objects large enough to cause civilization-ending damage, roughly once every several 100,000 to million years. We've been lucky recently, but luck runs out. Unless we develop the capability to detect and deflect dangerous asteroids, eventually our number will come up. Any civilization that doesn't master spaceflight and planetary defense faces this ticking clock. But these are relatively mundane threats, things we can at least imagine defending against given enough technology. Let's consider some truly exotic catastrophes. Vacuum decay is perhaps the most disturbing possibility. The universe, according to quantum field theory, exists in a particular vacuum state, a configuration of fields that represents the lowest energy state, or so we think. But what if our current vacuum isn't actually the true lowest energy state? What if we're in what's called a false vacuum, a metastable state that could decay to a lower energy true vacuum through a quantum tunneling process? If a false vacuum decay event occurred anywhere in the universe, it would propagate outward at the speed of light as an expanding bubble of true vacuum. The laws of physics inside this bubble would be different from those in our current vacuum. Atoms might not be stable. The fundamental forces might have different strengths. Everything in the path of this expanding bubble would be rearranged according to the new physical laws, which almost certainly means everything would be destroyed. The terrifying thing about vacuum decay is that there's no warning. The bubble wall approaches at light speed, so you can't see it coming. One moment you exist, the next moment the bubble reaches you and you cease to exist, along with your planet, your star, and everything else. There's no defense because the change occurs at a fundamental level of physics itself. Research into the Higgs field, particularly measurements of the Higgs boson's mass completed in the 2010s, suggested that we might indeed be in a metastable vacuum. The Higgs mass value we've measured is consistent with what we'd expect for a false vacuum, though with large uncertainties. If this is true, the universe could decay at any moment, or it might remain stable for trillions upon trillions of years. We simply don't know. Some physicists have speculated whether high-energy physics experiments could trigger vacuum decay. If there's some energy threshold above which the false vacuum becomes unstable, could we accidentally reach that threshold in a particle collider? The consensus is that cosmic rays, which regularly hit Earth's atmosphere with energies far exceeding anything we can create in laboratories, have already tested much higher energies without triggering decay, so we're probably safe. But there's an element of uncertainty that's philosophically troubling. Every time we probe physics at a new energy scale, we're rolling dice whose odds we can't precisely calculate. Then there are rogue black holes. Most black holes are relatively easy to track. They either form from the collapse of massive stars, leaving clear signs of their birth, or they sit at the centers of galaxies, where their gravitational effects are obvious. But theoretical work suggests that primordial black holes, formed in the early universe from density fluctuations shortly after the Big Bang, might exist and could be wandering through space essentially invisible until they get close enough for their gravitational effects to become noticeable. A stellar mass black hole passing through our solar system could gravitationally disrupt planetary orbits, potentially ejecting Earth from the habitable zone, or even from the solar system entirely. An encounter with a primordial black hole of smaller mass could still be catastrophic if it passed through Earth itself. The tidal forces near the black hole's event horizon would tear apart anything that got too close. The probability of such encounters is extremely low, given the vast emptiness of space. Black holes are tiny compared to the distances between stars. But over geological timescales, low-probability events become increasingly likely to occur eventually. Any long-lived civilization has to contend with the fact that unlikely catastrophes eventually happen if you wait long enough. There are even more speculative threats. Some theories in physics suggest the possibility of strange-lit matter, a hypothetical form of matter consisting of roughly equal numbers of up, down, and strange quarks. If strange matter is more stable than normal matter, and if a strange lay came into contact with normal matter, it could theoretically convert that normal matter into strange matter in a runaway chain reaction. A single strange lit could convert an entire planet into strange matter within minutes. These particles might be created in neutron-star collisions or in high-energy cosmic ray interactions. Again, the probability seems low, but we're not entirely certain strange matter can't exist or couldn't trigger such a conversion. The point of cataloging these catastrophes isn't to induce panic. Most of them are so unlikely or so far in the future that they're not immediate concerns. The point is to recognize that the universe is fundamentally hostile to life. We exist in a narrow band of conditions, a fragile equilibrium maintained only as long as nothing too extreme happens. Every civilization that arises faces this gauntlet of potential catastrophes. The longer a civilization exists, the more likely it is to eventually encounter something that destroys it. This might be part of the answer to the Fermi Paradox. Maybe civilizations are common. Maybe they even get past the great filter of self-destruction, but they're eventually eliminated by cosmic accidents. The universe is old enough that billions of civilizations could have arisen and been wiped out by gamma-ray bursts or vacuum decay events or encounters with rogue black holes. The silence we hear isn't necessarily because civilizations destroy themselves or hide. It might be because the universe itself is a minefield, and eventually every civilization's luck runs out. If this is true, it adds urgency to humanity's situation. We need to become multiplanetary, then multi-system, then eventually multi-galactic, if we want to ensure long-term survival. Concentration in one location, even concentration in one solar system, leaves us vulnerable to catastrophes we can't prevent. The only defense against cosmic accidents is redundancy, spreading ourselves across enough locations that no single event can wipe us all out. The universe isn't empty because no one ever arose. It's empty because the cosmos is deadly, patient, and ultimately indifferent to whether intelligence survives or perishes. That's a sobering thought, but it's also a call to action. If we want humanity and the legacy of Earth to persist, we need to take the threat seriously and act accordingly. The universe is empty for a reason, and that reason might be stalking us right now from the depths of space, invisible and inevitable. The Anthropic principle and observer selection effects. Let's shift to a different kind of explanation for the Great Silence, one that's less about what's actually out there and more about the nature of observation itself and the strange implications of being observers in the first place. This brings us into territory that brushes against philosophy as much as physics, the Anthropic principle and observer selection effects. The Anthropic principle, in its simplest form, states that the universe must be compatible with the conscious life that observes it. This might sound trivial, almost tautological, but it has profound implications when applied to questions about why the universe has the properties it does and why we find ourselves in the situation we're in. There are different versions of the Anthropic principle. The weak Anthropic principle simply says that the observable universe must have properties that allow conscious observers to arise, because if it didn't, we wouldn't be here to observe it. This is hard to argue with. If the laws of physics were dramatically different, if fundamental constants had very different values, stars might not form, or chemistry might not be complex enough for life, and we wouldn't exist to wonder about it. The strong Anthropic principle goes further, suggesting that the universe must have properties that make the emergence of observers inevitable at some point in its history. This version is more controversial because it seems to imply some kind of purpose or design, though it can also be explained through multiverse theories without invoking purpose. How does this relate to the Fermi Paradox? Well, consider an observer selection effect called the sleeping beauty problem in probability theory. If you are randomly selected from all possible observers, you are more likely to be an observer in a common situation than a rare one, simply because there are more observers in common situations. Applied to the Fermi Paradox, this suggests that if we're typical observers, we should find ourselves in a universe that's typical for observers to arise in. But what's a typical universe for observers? This depends entirely on how common observers are. If intelligent life is extraordinarily common, filling the universe with countless civilizations, then a typical observer should find themselves in a universe teeming with detectable aliens. The fact that we don't suggests either that we're not typical observers, or that intelligent life is actually quite rare, making our experience of an empty universe exactly what typical observers should expect. Nick Bostrom, a philosopher at Oxford who has written extensively on anthropic reasoning and existential risk, has analyzed this problem in detail. He points out that observer selection effects can dramatically skew our expectations. For example, if there's some great filter that most civilizations don't pass, observers like us will necessarily find themselves before that filter, because observers who encounter the filter don't survive to ask questions about where all the aliens are. This is called the doomsday argument in some contexts, and it's deeply unsettling. Here's how the doomsday argument works. Imagine all humans who will ever live, past, present, and future. You are one random human drawn from this group. If humanity goes on to colonize the galaxy and exists for millions of years, there will be trillions of humans in total, and you're surprisingly early in that sequence, which seems unlikely. But if humanity is close to its end, with only a few more generations to come, then being alive now makes perfect sense. You're somewhere in the middle of humanity's existence. By this logic, we should expect humanity to end relatively soon rather than persist for millions of years, simply based on our temporal position in the sequence of all humans. The argument is controversial, and there are many proposed resolutions and objections to it. But it highlights how observer selection effects can lead to counterintuitive conclusions. Applied to the Fermi Paradox, it suggests that we might be fooling ourselves about the universe's emptiness. Perhaps the universe isn't empty at all, but observers like us, who exist before making contact with other civilizations, are far more numerous than observers who exist after such contact. If first contact typically leads to bad outcomes, then most observers find themselves in an apparently empty universe, simply because those who discover they're not alone don't survive to report it. This brings us to an even more unsettling possibility: the simulation hypothesis. What if we're not living in base reality at all, but rather in a sophisticated computer simulation created by some advanced civilization? This idea, popularized by philosopher Nick Bostrom in his 2003 paper, Are You Living in a Computer Simulation?, suggests that if it's possible to create high-fidelity simulations of conscious beings, and if advanced civilizations have any interest in running such simulations, then simulated realities might vastly outnumber base reality. Think about it this way. In base reality, there's presumably one universe with perhaps one or a few advanced civilizations. But each advanced civilization could run millions or billions of simulations, each containing conscious entities who believe they're in a real universe. Numerically, the simulated entities would vastly outnumber the entities in base reality. If you are a random conscious observer, you're much more likely to be in a simulation than in base reality, simply because there are so many more simulations. How does this explain the Fermi Paradox? Well, if we're in a simulation, the universe might appear empty simply because the simulators chose to create a simulation of an isolated civilization. Perhaps they're interested in studying how a civilization develops without outside interference, how it responds to the apparent emptiness of the cosmos, whether it destroys itself or reaches some kind of sustainable equilibrium. The simulation might be designed specifically to not include other civilizations, or to make them undetectable, because that's the scenario being modeled. This is philosophically troubling because it's fundamentally unfalsifiable. If you're in a sufficiently sophisticated simulation, there's no way to detect it from inside. Any test you can devise could be simulated. Any physical law you discover might be programmed rather than fundamental. The simulators could intervene to maintain the illusion whenever necessary, or they could simply be running a simulation sophisticated enough that it doesn't require intervention. Some physicists have speculated about potential signatures of simulation, like finding computational limits in the universe's resolution, similar to pixels in a video game. If space-time is quantized at the Planck scale, if there's some maximum information density, these might be hints that we're in a computational system. But these features could also be genuine properties of base reality, so they don't prove simulation. The multiverse adds yet another layer of observer selection effects. If there are infinite or near-infinite universes with different physical laws and initial conditions, then we should not be surprised to find ourselves in one of the rare universes that can support life, because we can only exist in such universes. This is sometimes called the weak anthropic principle carried to its logical conclusion. But multiverse theories also suggest disturbing possibilities. In an infinite multiverse, every possible history that could occur does occur somewhere. This means there are versions of you in universes where Earth is teeming with detected alien civilizations, and versions in universes even emptier than the one we observe. The fact that you find yourself in this particular universe might be random chance, or it might be determined by some measure of which universes are more likely to contain observers like you. Quantum mechanics introduces even stranger possibilities through the many worlds interpretation. If every quantum measurement splits the universe into branches where all possible outcomes occur, then there are branches where we have detected alien signals and branches where we haven't. We find ourselves in this branch not for any deep reason, but simply because this is one of the many branches that exist. The universe isn't empty. It's just that in this particular branch of the quantum wave function, the specific historical trajectory happened to not include alien contact yet. All of these anthropic and observer selection arguments can feel like they're cheating, like they're explaining away the paradox without actually explaining anything. They often invoke unfalsifiable hypotheses, scenarios we can't test or verify. But they serve an important function. They remind us that what we observe might not be representative of what exists. Our perspective is necessarily limited and biased by the fact that we can only observe from our particular vantage point as conscious beings who evolved in this specific situation. Here's the truly terrifying implication of all this anthropic reasoning. We might be fundamentally unable to know whether the universe is empty or full, whether we're doomed or destined for greatness, because our very existence as observers selects for certain kinds of universes or situations. If the great filter is ahead of us, we would expect to find ourselves before it, in an apparently empty universe. If civilizations that make contact with aliens are typically destroyed or absorbed, we would expect to find ourselves isolated. If we're in a simulation designed to study isolated civilizations, we would expect to see no aliens. If we're in a universe that's rare for some reason, that rarity might be precisely why observers can exist here. The anthropic principle and observer selection effects don't resolve the Fermi Paradox so much as they complicate it, adding layers of uncertainty about whether our observations and expectations are even reliable guides to what's actually out there. They suggest that the universe might be empty for reasons that have nothing to do with filters or dark forests or timing, and everything to do with the strange logic of observation itself. In a sense, these arguments are the most unsettling of all, because they suggest that we might be trapped in a kind of epistemic prison, unable to reliably reason about our place in the cosmos because our very existence biases the data we can collect. The universe isn't just empty. Our observation of its emptiness might be fundamentally misleading, a perspective artifact that tells us more about the nature of observation than about the nature of reality. And that thought, that we might be wrong about something so fundamental in ways we can't even detect, is perhaps the most terrifying implication of all. What the emptiness means for humanity. So, where does all this leave us? We've explored a multitude of explanations for why the universe appears empty. Maybe life is rare. Maybe intelligence is rare. Maybe there's a great filter that destroys civilizations before they spread. Maybe civilizations hide from each other in a dark forest. Maybe we're early and expanding civilizations haven't reached us yet. Maybe cosmic catastrophes eventually eliminate everyone. Maybe observer selection effects mean we're systematically misunderstanding what we see. Or maybe it's some combination of all these factors, a perfect storm of improbabilities and dangers that makes intelligent civilizations a perfect storm of improbabilities and dangers that makes intelligent civilizations appear as fleeting sparks in an eternal night. But if the silence is indeed absolute, it forces us to confront a terrifying yet exhilarating possibility. We might be the only ones. Our responsibility as the potential first civilization. If we are the firstborn of the cosmos, the weight of the future doesn't just rest on our shoulders. It begins with us. In a universe that is $13.80 billion years old, we emerged in a relatively young window of cosmic habitability. Most Earth-like planets are yet to be born. If we are the vanguard, we are not just observers. We are the pioneers of the life era. Our responsibility is no longer just to our nations or our species, but to the concept of complex life itself. We are the stewards of a rare biological miracle. If we fail, the light of reason might go out in this sector of the galaxy for billions of years. We must act as the guardians of the only flame in a vast, dark cave. Loneliness and cosmic purpose. Loneliness is often seen as a void, but in a cosmic sense, it is a call to action. Without other voices to guide us, we must invent our own purpose. The universe provides the stage, but it does not provide the script. Our cosmic purpose is to be the eyes and ears of the universe. When we look at a galaxy like Alcyonius spanning 16 million light-years, we see a structure of unimaginable scale. Yet, without a mind to perceive it, that galaxy has no name, no beauty, and no meaning. Our loneliness is the price of our uniqueness. We give the void its value. The burden of consciousness. Consciousness is a double-edged sword. It allows us to calculate the orbit of distant stars, but it also makes us aware of our own finitude. We are a collection of atoms that can think about atoms. This is a heavy burden because it means we are the only part of the universe that can suffer, hope, and feel the existential dread of the great silence. This burden requires us to transcend our tribal instincts. If we are the universe's only way of knowing itself, then every war we fight and every resource we waste is a betrayal of our cosmic status. We are the great filter ourselves. Our challenge is to survive our own technological adolescence, future possibilities and conclusions. The emptiness is not a wall, it is a frontier. If the great filter is behind us, the future is limitless. We could become a Type 3 civilization on the Kardashev scale, harnessing the energy of entire galaxies. We could spread Earth's biology to sterile worlds, turning the emptiness into a garden. The conclusion is simple but profound. The universe's silence is not a rejection of humanity, it is our inheritance. It is a vast, open space waiting for us to fill it with meaning, art, and life. The sheer scale of the largest galaxy we've discovered is enough to make any human feel insignificant. But remember this: a galaxy, no matter how vast, is just a collection of gas, dust, and gravity. It cannot feel, it cannot dream, and it cannot wonder. The emptiness of the universe isn't a sign of our insignificance, it is an invitation. It is a vast, open canvas waiting for a story to be told. We are the authors of that story. Whether we remain a footnote on a single planet or become a chapter that spans the stars depends entirely on what we do next. If this journey into the void changed the way you look at the night sky, consider sharing it. We are all in this silence together. What do you think? Is the emptiness a warning or an opportunity? Let's discuss in the comments below. Stay curious and keep looking up.